Hello, I am Anurag Tripathi. I am a faculty member in the Department of Physics at IIT Hyderabad, and I will be the instructor of this course, which is Introduction to Quantum Field Theory. We will be mainly covering here theory of scalar fields. Okay, so I would not be doing quantization of fermionic fields or gauge fields in this course, and this will be mostly, in fact, solely canonical quantization, which will be covered in this course. And this is a 30 hours course which will run for 12 weeks. And the formulation that we are going to develop here, okay, the framework of quantum field theory that we develop here, it can be applied to theory of fermionic fields as well. So you could construct, for example, electrodynamics using it, but we will restrict to scalar fields, as I said. And there are few prerequisites for this course. Let me write it down. Okay, so here are the prerequisites. I am not so sure about the spelling. Requisites. Hopefully it's correct. So you should have encountered quantum mechanics in your master course. Okay. And then, of course, special relativity. And then you should have also studied classical mechanics in your master's course. Meaning you should be familiar with the concept of action, how to obtain equations of motion using variational principles from the action. Okay, so principle of least action that you should know, how to construct Hamiltonian and other related things. So these three courses you must have taken. Okay, and to have some idea of fields, it will also be useful if you have taken a course on electrodynamics. Okay, so these three together form the prerequisites for this course. Okay, then you should know how to construct a quantum theory given a classical theory. So it might have been covered in your quantum mechanics course, but let me nevertheless mention here. So suppose you have some system which is described by generalized coordinates, which I label as Qi, okay, and where I runs from 1 to n, where n is the degrees of freedom that system has. And P's, it's too big. Pj's are the momentum conjugate to the variables Qi, okay, to the coordinates Qi. So these are your canonically conjugate variables. Okay, and this is at the classical level. Now, to make a quantum theory for the classical system which is described by these coordinates, okay, what you have to do is replace the Poisson brackets by commutators, and you have to throw in a IH bar. So you should have also studied Poisson brackets in your course. So if you construct Poisson bracket of Q with a P Okay, this curly brackets I am using to denote Poisson brackets, and if you do so, you get delta I j. Okay, and of course the Poisson brackets of Q with itself and P. Okay, let me write down Poisson bracket. So this is one relation, and of course the other ones are these. So a Poisson bracket of a Q with another Q or with itself is 0. Similarly, for the conjugate momentum P, is 0, and Q with P is non-zero when Q and P are conjugates of each other. Okay, if the index I and j are different, then of course it's 0. So the prescription for going from the classical description to quantum mechanical description is this. Let me write it down here. So this is classical mechanics, and you want to make a quantum theory here. So what you do is, first you promote all the coordinates, all the Q's and P's to operators. So they become operators now. Okay, that is what the hat is indicating, that these are operators. And the Poisson brackets are replaced by commutators. So you define Qi hat, Qj hat, commutator is 0, that you would have already studied in your quantum mechanics. Similarly, Pi hat, Pj hat is equal to 0. Okay. So what we are doing here is, okay, let me write down this one and then it will be clear what I am doing. Pj. Okay. So you form this commutator, sorry, Pj. Then this thing is replaced by, or it is equal to IH bar, the Poisson bracket you calculated in the classical theory. Hat. Let's check. That's correct. Okay. And what did you calculate? Qi hat Pj hat was delta Ij. So it becomes IH bar delta Ij. Okay, where delta is the Kronecker delta. So if you are looking at Q comma P, where Q and P are conjugate variables, then it just becomes IH bar. Okay, and that's the commutator you have in quantum mechanics. Okay, so that's the prescription. How you make a quantum theory starting with classical theory? You take the coordinates, take the conjugate momenta, calculate the Poisson brackets, and to make the theory in quantum theory, you promote them to operators, define a commutator, and commutator will be the same as your Poisson bracket in the classical theory times IH bar. Okay, that's how you make quantum theory out of a classical theory. That's the prescription. Okay, so this you should keep in mind. This we are going to use several times, and most likely you have already encountered this. Okay. So this forms the prerequisites I have listed down in some material here. Let me mention some of the books that you can refer to, and which I will also use in this course. So let me write here on the next page. I will not write the titles, I'll just write the names. So you have a book by Peskin and Schroeder. Schroeder. Okay, the title is An Introduction to Quantum Field Theory. Okay, Another book is by Anthony Z. It's a very nicely written book. Okay, its title is Quantum Field Theory in a Nutshell. Then you have Weinberg. So there are 3 volumes to this series, and the one which will be most useful for this course is the Quantum Theory of Fields, Volume 1. You have book by George Sturman. Okay, it's called An Introduction to Quantum Field Theory. That's also a very, very nice book. It goes into details which are usually not covered in other books, so I would also recommend this book. You have Ityxen and Zubair. Itzykson. Ityxen and Zubair. That's also a very nice book. And of course, you have lectures by Ashok Sen. You can visit his web page, and you'll find his lectures there. And there is book by Raymond. Okay, this is called Field Theory, a Modern Premier. Okay, and of course there are many other books which have come recently in last few years, and you can also refer to them. Okay, so these are all the references that I have. Okay, good. Then let's ask why we are going to study this course. What's the requirement of having quantum field theory? Okay, to set the stage for this course, imagine this. You have an electron and a positron. Okay, positron is an antiparticle of the electron. Okay, and these two particles are rushing towards each other at very, very high speeds, speeds that are very near to the speed of light. Okay, so they are coming with enormous speeds, so there's a lot of energy in this system. Okay, and they collide. This is something which was done at the LEP, for example, Large Electron Proton Collider. Now when this collision happens, both the electron and the positron, they disappear. They do not exist anymore. Okay, what is produced is a variety of particles. Many things are produced. Okay, you can be producing Higgs bosons, you can be producing photons, okay, W boson, Z boson, okay, even quarks, antiquarks, and gluons. So you could be producing all these things which were not there to begin with. And what was there to begin with, that electron and that positron, that disappeared. Okay, now if you want to describe this system, it's time evolution. Okay, the quantum mechanics or single particle quantum mechanics that you have learned is not going to work. Okay, it's not going to work for a simple reason, because when you set up those equations, like Schrodinger equation, for example, okay, the wave function psi in there describes the probability of finding a particle, let's say that electron and that positron, whichever one you choose, in space and time. Okay, and you remember if you take that wave function psi, you have to normalize that wave function, of course, but then the interpretation is that it represents a probability density, and if I integrate over the entire universe, I get 1. Meaning, let me emphasize this a little more by putting these arguments. Okay, meaning this particle exists somewhere in the universe at all times, right? But the process that I described, there that electron disappears, it's not there anymore. And not only that, new particles were created. But here you have this requirement that the particle has to exist at all times. So you cannot deal with creation of particles or annihilation of particles using single particle quantum mechanics, for example, your Schrodinger equation. Okay, so that's not going to work. And clearly we need a different formalism to deal with such situations, and that formalism is that of quantum field theory. So idea is the following. What we'll do is we will treat that psi you get here, okay, that is the wave function which satisfies Schrodinger equation. We will treat it as a classical field. Okay, we'll say, okay, even though we got it because we are doing quantum mechanics, but now good, I don't want to treat it as a quantum mechanical thing anymore. I'll say it's a field which is satisfying some equation, which is Schrodinger equation, but I'll treat it as if it is something classical. Okay, and then I will quantize that field. Okay, and it works, it does what we need, and you will see that that happens in the course. Okay, now how to get this idea is a separate issue, but let's say we accept that this is really working, we can check. Then let's proceed with quantizing of fields rather than quantizing the coordinates. Okay, earlier you were quantizing the coordinates, you were saying you have q, you have p, and you put a commutation relation, but here you will now be quantizing the fields. Okay, so that's what we are going to do now. So let's begin. So first, very quick review of what you already know. So even though we want to have field theory which is relativistic, because these particles were moving at great speeds and you need relativity, let's start with something which is familiar to everyone. Let's start with Schrodinger equation. Okay, and we'll worry about bringing in relativity later. So let's start with our very familiar Schrodinger equation. So what's the Schrodinger equation? It's I h bar del psi xt over dt is h psi. Okay, I will use a small h because I'm going to use capital H later. Okay, here small h is the Hamiltonian of this system, okay, which we are studying. So you know what h is, where, let me write down here, maybe here itself. So h is minus h bar square over 2m, and you have a gradient square. Okay, that's a scalar quantity. Remember, there is a dot product here, so it's scalar under rotations, plus the potential term. Okay, and this h is your operator. Okay, so we are imagining system which is described by some potential v. Okay, and you have some particle in there, and the wave function of that particle is given by psi x of t. Okay. So I am doing the old thing which you all know, and here let me also write down the eigenfunctions of H. So if you take H, its eigenfunctions, let's label by un of x comma t, now un of x, okay, and because it's a Hamiltonian, the eigenvalue will be energy, denoted by E, okay, En un of x, okay, and n runs typically, it takes infinite values, so and 1, 2, 3 up to infinity, okay. Okay, and let me write down your un, they are eigenfunctions. Okay, of the Hamiltonian H, and they form a complete set. They form a complete set because they are eigenfunctions of this Hermitian operator H, okay, because the operator is Hermitian, that's why this is fine. And because they form a complete set, I can write psi as a sum of these functions, okay, as a linear sum of these functions. So I can decompose psi as an, okay, an of t un of x, and there is a summation over all the n, okay. That's what we can do because un forms a complete set. Okay, and as I said before, this cannot handle creation and annihilation of particles because of this reason. Mod psi square x, it has to be somewhere at all the times, it cannot disappear. Okay, good. Now, as I was saying, we will make a departure from the way we interpret psi. Okay, so we are going to make a departure in interpreting psi. Okay, so I don't want to treat it as a wave function of anything. I do not want to say that psi describes wave function of a particle which is moving around in potential v. I don't want to do that. I just want to say psi is a classical field which satisfies this equation. Okay, that's what I want to do. Okay, one remark I wanted to make here was, it's a side remark, it's not really falling in the line of argument, but note that this equation cannot describe an electron, for example. You see, an electron, you know, has spin up and a spin down, it has spin, okay. So psi only gives you a number, or actually two numbers because it's complex, so I have a real part and complex part at each space-time point. So at x and at this value of x, at this value of time, psi has this value, okay. So with just this information, it cannot tell I mean, there is no information or there is no provision here in this way it's written up to distinguish between whether that electron has a spin up or spin down, or it's in some linear combination. Okay, that information is not present here. So this you can think of describing a particle which does not have any internal degrees of freedom. Okay, an electron has internal degrees of freedom. In addition to where it can be, it can also be in those other states which are permissible. So it could be here and be in spin up or spin down or whichever way. Okay, so that internal degrees of freedom, they are not present in this equation. But anyway, that's besides the point. So as I was saying, we will make a departure in interpreting psi of xt, and we are going to treat it as a classical field. So we will treat it as a classical field. And now, of course, because we are not going to treat it as a wave function, this is not a probability density of anything. Okay. Good then. So what should we do? I want to write down the classical theory which has Schrodinger equation as the equation of motion. Okay. Which means I should be able to construct an action from which I can derive Schrodinger equation as the equation of motion. Okay. What does it mean to specify a system? It means that you give the action of that system. Okay. Once you give the action, everything else follows. Okay. You can use variational principles. You can extremize the action, find out the equation of motion from there, construct the Hamiltonian, whatever you wish, and that's what means to specify a system. So let's do that. So the goal now is to write down the action which will give this as the equation of motion. Okay, this as the equation of motion. So let's see. Okay, so here is the goal. I am looking at I'm searching for an action of a system. Find action that gives Schrodinger equation as the equation of motion. That's what we want to do. Okay, note that the system which we are going to construct will have infinite degrees of freedom because your psi describes that system, and psi is a field. Okay, so let's see why it is an infinite, it's a system of infinite degrees of freedom. So if you write psi x of t as un x and these coefficients a n of t, okay, that's the decomposition you saw before also. So if your system is described by psi, you see it's effectively described by a. So the UNs are wave functions, they are fixed. You have found the eigenfunctions of the Hamiltonian, that small h. Okay, these are fixed, so you know what is u1, you know what is u2, what is u1 billion, you know those, so they are there. The freedom that you have is in choosing ANs. Okay, so they are the generalized coordinates for this system now. Okay, and because there are infinite of them, you have a system of infinite degrees of freedom. Okay, that is good. And your ANs are the generalized coordinates. Okay, that's good. Now let's go back to our desire to have an action for this theory. So we do the following. So I want to construct the action which will give this as the equation of motion. So what did we have? We had I h bar del psi over del t minus h psi is equal to 0. Okay, so this is what I want to get from action. So let me construct the action. You see, this is what I should get when I do a variation. Okay, so let's do this. So I construct S as integral dt over a Lagrangian. Okay, and that Lagrangian I write as d cube x times this psi star xt. Okay, and then I put this thing which you have here. Okay, this entire piece which you have here, multiplying psi star, and you will see immediately why I am doing that. Okay, let me make a square bracket. I h bar del psi over del t, and psi is at xt, minus h hat. H is the operator, so h okay, maybe in the next term I will specify it more, but here it's fine. Okay, plus psi xt times I h bar del psi xt over del t minus I started doing something wrong. That's why I was feeling strange that what am I doing. Okay, so here is your action. Okay, now you can see why I have constructed it this way. When I take a variation with respect to psi and psi star, I will get this as the equation of motion. Okay, let's see. You see, your psi is a complex function, right? So your psi is a complex field, so it has a real part and an imaginary part. Okay, so you can, at each point you have two numbers, psi r, and they both are independent of each other. So you can use them as independent fields and do a variation, or you can choose to instead work with psi and psi star. It's identical. Okay, whether you work with psi r and psi I, or whether you work with psi and psi star, because you can always write psi r using psi and psi star, psi I using psi and psi star. Okay, so both are equivalent. So we'll work with psi and psi star. So if I am looking at delta S, a variation of S, okay, I'll get the following. So you have dt d cube x, and then I do a variation of psi star, and then I do a variation of psi. So this is what we get when we do these variations. So you have delta psi star. I'm doing exactly what you do for you have learned in classical mechanics. okay, and then you have I h bar delta psi over delta t minus h psi xt plus, now you take the term psi star xt, I am suppressing x and t in other parts, and then you have variation in this piece I h bar delta over delta t of delta psi. Okay, I'll suppress the other arguments, minus h, the Hamiltonian, delta psi. Okay, maybe I should be more clear in this. Okay, here it's the Hamiltonian is minus h bar square over 2m gradient square, and this is acting on plus v of x, and this entire thing is acting on psi, right, and that has become delta psi for us. Okay, good. Now if I take if I put delta s to 0, and because delta psi star and delta psi are independent of each other, I will be able to find the equations of motion. Okay, so first term is good, everything is fine here because you have a delta psi star. The second term is not so nice because you have a delta psi on which several derivatives are operating. Here delta t is time derivative is acting. Here you have differential operator del square acting on delta psi. So what we want to do is we want to free up the delta psi of all these operators. So we want to pull them away, and it's easy to do using the method of integration by parts. Okay, so I'll do the integration by parts which you have learned in your school. Okay, simple thing. So that's what I'm going to do. So nothing has to be done here, only I should do something here. Okay, and remember what integration by parts does. When you integrate by parts, you take derivative from one factor and put it on the other factor, and you pick up a minus sign. So every time you pull a derivative and put on the next factor, okay, you pick up a minus sign, and of course there are boundary terms which you generate, which I will leave for you to figure out why I'm not writing those. So let me write it down now. Maybe I can tell you here itself. You see, you have a delta over delta t. So when you do integration by parts, this delta over delta t will shift to psi star. So this will become delta psi star over delta t, and you will get a minus sign. Okay, then when this term is fine, v delta psi, there is it's okay, it's good. This one which has a delta square is two derivatives. It's del dot del, and del is basically del over del x. Okay, so when you pull one derivative and put on psi star, you pick up one minus sign, but you are still left with one more del. When you pick up that one and put on the psi star, you have another minus sign. So that minus and minus makes a plus. Okay, so neither this term is going to generate a sign nor this term. This anyway remains the same. Okay, so these two are not going to generate any negative signs, only the derivative gets transferred to psi star. This one will generate a minus sign. Okay, because there is only one derivative here. So the answer is this. Let me write down. I hope I can. Let's see. Delta S is integral dt d cube x. The first term was easy, I can remember. Delta psi star, and what you have in the bracket is basically what you will eventually get as equation of motion. So that is minus, no, not minus, I h bar delta psi over delta t minus h, which is the Hamiltonian, h psi, okay, plus the other term, let's go back. How do I go back? Yeah, here. So this will become minus, because of being transferred, so minus I h bar del over del t acting on psi star, and you will have a delta psi, okay. So let's go here. So plus delta psi, which I have pulled out, minus I h bar del psi star over del t, okay, that's fine. And for this one, you will have delta psi will be freed up, which we have already written as a factor outside, and you will have, is a minus sign, so that we should take care of, and then this space. So you will have minus what was that, h square h bar square over 2m, okay, del square acting on psi star, and plus a v of psi star. So I can plus v of x psi star, okay. These things are now acting on psi star x of t. Okay, that's good, and I hope everything is correct here. It is, okay, fine. Okay, now good. Now I have freed up delta psi star and delta psi here, and because these are independent variations of two independent variables, the only way delta s can be 0 is if these two factors, okay, in the round brackets, they vanish by themselves. So I get the equations of motion I h bar delta psi over delta t minus h psi, which is your Schrodinger equation, right? So is equal to 0 I can put, or let me put equal to here. So I take it to the right side, and the other equation I get from here. So I get two equations of motion, minus I h bar delta psi star over delta t is equal to h psi star. Okay, this is h. This is your Hamiltonian h. And as you realize, this equation, the second equation, is just the complex conjugate of the first one. So it's not a new equation, it's coming from this one. And when you're taking complex conjugate, that I becomes minus psi and psi becomes psi star. Hamiltonian is, there's no complex conjugation involved here, and psi becomes psi star, okay. So I have got the equation of motion starting with this action, which means that the action I wrote down is correct, because it's giving me correct equations of motion. And you see how I have built it. So I have just taken this piece, this left hand side of the equation, and put it here and multiplied with psi star. Okay, this you can always do, and you will be able to construct the action if you know the equations of motion. Okay, very good. So where we are now, we have the action. Let's see what else. Okay, so I was asking you to think about the boundary values. Okay, let me just tell you very quickly about integration by parts in case you have forgotten. It's the simple thing. If you have a function f times g, okay, and you look at d over dx, the derivative of the product, then it is df over dx g plus f dg over dx, okay. And if I integrate, if I integrate on both the sides, okay, you see that here the derivative is on the first factor f, which you can write as a derivative on the second factor, okay. That is what we have done, and because this term you have to take to the other side, there is a minus sign which we have used, and this is the one which generates the boundary terms, okay. If you put some a to b, that is the one which is generating boundary terms, and that is what I am asking you here to think about. Okay, so we'll continue further looking into the system in the next video.